In this video, we're going to take a look at section 6.1 on the standard normal distribution. Now, before we get to the standard normal distribution, we start off by introducing this concept called a uniform distribution, just to kind of help you understand the concepts behind how we represent continuous random variables as probability distributions. And a uniform distribution, the math is a little bit easier than what we're going to have to do for the normal distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of probabilities. The graph of a uniform distribution results in a rectangular shape. Right, so what we're going to do is we're going to graph the probabilities because we can't list them on a table. And I guess there is a formula that kind of describes these probabilities, but it's a very, very complicated formula. And even with that formula, we still have to use, some pretty advanced mathematical techniques to get probabilities out of it. So it's not just a formula where you just plug the numbers in and it tells you the probability. You have to do something else with it. And I'll tell you more about it here in just a few minutes. The reason we can't list it on a table is because we're talking about a continuous random variable, which will have an infinite number of possible values. So we can't list an infinite number of values on a table and have their corresponding probabilities. There's a few issues with trying to do that. So instead, we're going to have a graph to visually represent the probabilities, but it may not be quite what you think. We're going to use the graph in a way that's different than what you would have done with graphing in college algebra. All right, so the graph here will be a rectangular shape. So it's going to look something like this. All right, so we'll have an x-axis and we'll have a y-axis. And the graph, now normally it's drawn from off the y-axis, but that's because we kind of just zoom into wherever the graph actually exists. If you actually had this centered at 0, 0, it could be somewhere over here, but it'll just be like a rectangular box like this. Right? And here are the range of possible values for the random variable. It starts here and it ends here. So for example, if we say that the smallest number for the random variable is 4 and the largest number is 10, then the graph for that probability distribution, if it's a uniform distribution, would be a rectangle that goes from 4 to 10, and it doesn't exist anywhere else. All right. Now, that tells you one dimension of the rectangle, right? We know the width of this rectangle is 6 because it goes from 4 to 10, right? That's a gap of 6, so that's the length of that. However, for the probability is not, so I'm trying to think of the best way to kind of ease you into these concepts. The probability is not a point on the graph. It's not like, okay, the point here is this right here. Like for x equals 4, the point is this, so the probability is like the y-coordinate. It doesn't work that way, right? This graph is actually a probability density function. So a density curve is the graph of a continuous probability distribution. And here's how it encodes the probabilities for the different possible outcomes of the random variable. The total area under the curve down to the x-axis must equal 1. Now that should let you know there that it's the area that is going to correspond to the probability. Not a point on the graph, but the area from the graph down to the x-axis. Because we know the total probability has to equal 1. And we are requiring that the total area under this graph equal 1. So there's a connection there between area and probability. Every point on the curve must have a vertical height that is 0 or greater, meaning you can't have a negative probability, right? You can't have a negative probability density, which would give you negative areas, right? So if we measure the area from the graph down to the x-axis, and if we had some of the graph below the x-axis and we measured that area, well, the area below the x-axis would kind of negate the area above the x-axis. And that's not allowed to happen because that would sort of indicate a negative probability being applied. And as we've talked about, probabilities can't be negative. So again, there's a connection here between the area and probability in that we can't have a negative counting area because we can't have negative probabilities. right? And then the area under the curve between two x values will correspond to the probability of getting a result between those two x values. So a requirement of the density curve is that the area under the curve between two values has to correspond to the probability of getting a value between those two values, right? Or getting a result between those two values. Saying values multiple times makes it sound a little more confusing. All right, so going back to the drawing, the area is not this point. I can't say, oh, what's the probability of getting 5? Well, let's look at this point and see what it is. It doesn't work that way. In fact, you can't even ask, what's the probability of getting exactly 5? Because there's no area to measure. If I look at the space beneath the graph just for x equals 5, it's just going to be this vertical line, which has no depth to it, right? It has no width to it. So there's no area to measure. So this is how infinities make things weird. Because there's an infinite number of possible values, you cannot assign a non-zero probability to any of them. Because if you give an infinite number of values a non-zero probability, when you add up all those non-zero probabilities and there's an infinite number of them, it'll add up to an infinite amount of probability, which is not allowed, right? Probability has to be limited to equaling just 1. And so when there's an infinite number of possible values for your random variable, the probability of getting any one of those in particular has to be 0. And it's a weird thing, but math bears this out, that if you add up an infinite number of zeros, it can add up to something non-zero. So even though the probability of any one particular number occurring is 0, there's an infinite number of possible values, and all of those infinite 0 probabilities add up to a non-zero amount. But you're not going to get a satisfactory answer from this. So if you ask, what's the probability of getting exactly 5? It's actually, the probability is 0. You have to give a range of values to get a non-zero probability. And so we could ask, for example, what's the probability of getting a number between 4 and 5? And the probability of that occurring corresponds to the area under the graph down to the x-axis between 4 and 5. So this area that I've just shaded in corresponds to the probability of getting a value of x between 4 and 5. Right. Now to calculate that probability, it's an area, and this is why we want to start with uniform distribution, because we know how to calculate this area. It's a rectangular shape. We know the area of a rectangle is length times width. Right? And we already have the width. I guess that's the total width. I shouldn't be pointing to that. The width of the area I've shaded in is just a 1, right? So between 4 and 5, if I want to find the area of what I've shaded in here, the width is 1, right? So that'd be the width. But what's the length? What's this part here? And I don't know which one I should call the length or the width. It really doesn't matter mathematically speaking, but I'm sorry if that seems backwards. Now that I'm thinking of it, maybe I should call this the length and this one the width, but it doesn't matter which one's which. I need to know what this dimension is to find the area. I know this one is 1. I need to know what this one is. That's where this number comes into play. So this is the width of the entire rectangle. The requirement here for the uniform distribution is that the total area, so I'm going to shade in another area. I'm going to try to use, I never use yellow, but let me try yellow here. So, oh, that's really hard to see. That was a bad choice. Let me pick, well, green's already in use. Red's the, I'll use black, I guess. So this area here, right? This total area has to equal 1 for this to be a probability distribution function, right? Or a density curve. To be a density curve, the total area has to equal 1. And so we can figure out what this height is by considering that the width is 6 for the entire rectangle, and then plugging that into the formula for area. Because I know the area has to equal 1. That's going to be length times width. The length we are trying to find out, we don't know what that is, but the width we know is 6 for the entire rectangle. And we know the area has to equal 1. And then I can solve for L by dividing 6 on both sides, and I get that the length would have to be 1/6, right? So this dimension here is 1/6. It goes from 0 up to 1/6. So this has a a width, or a length, excuse me, of 1/6. So to find the original area here, the one I had colored in green, the probability of getting a number between 4 and 5, the length there is 1. I keep getting these backwards. The width is 1, but now we know the length is 1/6, and we get that by considering the entire rectangle to figure out that length. And that's not going to change. So even when I shrink it down to just being between 4 and 5, this dimension will stay the same. It'll be 1/6 in order for the entire rectangle to have an area of 1. And so the length will be 1/6. Oh, I can't write my sixes today. I don't know. Seems like every time I do a video, there's some number. Oh, I just messed up. I hit the wrong button. There's some number I can't write properly. So let me try that again. So 1/6. All right. And we multiply these together. And 1/6 times 1, of course, kind of boring math, but we get 1/6. So for this uniform distribution that runs from 4 to 10, the probability if I randomly select one number that it's between 4 and 5 is going to be 1/6, because that's 1/6 of the total area. So the probability of getting a number in that area would be 1/6. An analogy that the textbook gave one time, I don't know if it's still in the current edition of the textbook, but it was there once upon a time, is you can kind of think of this like throwing darts, right? So if you were going to throw a dart at this graph and you knew it would land within the rectangle, what's the chance that it would land between 4 and 5? Well, again, because that's 1/6 of the total area, there's a 1 in 6 chance it lands between 4 and 5. So when we're randomly picking a number between 4 and 10 from this uniform distribution, it's like throwing a dart at it. And whatever, so to find the corresponding probability that it's between any two given numbers, it's equal to the proportion of the area that space takes up out of the total area, just like it would be if you're throwing a dart at it. So that's how the uniform distribution works. So let's take a look at a homework problem. I'm sorry, this one's kind of hard to see. I'll zoom in, but I kind of did a funny thing there. All right. So the waiting times between a subway departure schedule and the arrival of a passenger are uniformly distributed between 0 and 8 minutes. Find the probability that a randomly selected passenger has a wait time less than 0.75 minutes. All right, so we're told this is a uniform distribution, so you should immediately think of a rectangle as representing the density curve for that uniform distribution. And it's going to go from 0 to 8, right? So the range of possible values are from 0 to 8, and the probability is equally distributed among those values, right? And so it's going to be a rectangle going from 0 to 8. And so this would be the probability density here. This is our random variable, our possible data values. Now this time, in order to find this probability, we want to find the probability that x is going to be less than 0.75. So 0.75 is going to be like right here. And to find that probability, it's going to be the area from 0.75 to the left, right? Because we want to know the probability that the wait time is less than this number. The wait times that are less than 0.75 are to the left of 0.75. So from 0.75 all the way to the left, whatever that area is, that's the probability that the wait time is less than 0.75. So I need to find that area. The length or the width, whatever one you want to call it, so again, it's going to be, because it's a rectangle, it's length times width. The width here is 0.75, right? Because it goes from 0 to 0.75. So that's the width. But again, the length we're not given. They don't tell us in the problem, here's the length of the rectangle. We have to calculate it using the range of values for the entire rectangle. So we have to remember that the total area is equal to 1, right? So this is the total area of the entire rectangle. So from 0 to 8, if I look at the area of the entire rectangle from 0 to 8, that area has to equal 1. And I know because it's a rectangle, it's equal to length times width. For the entire rectangle, the total width is 8. So I can plug that in for W, and then I can solve for L. I divide by 8 on both sides, and I get that this time, the length has to be 1/8. Right? So that is the measure of the other dimension, right? This is going to be 1/8 here. So if you want to think, to me, height actually makes more sense, but that's not part of the formula for a rectangle. But, you know, the height is 1/8, right? And the length here is 8. And that way, when you multiply these together, 1/8 times 8, you get 1 as the total area. Now, when I shrink it down to just from 0 to 0.75, because that's the probability I'm trying to calculate, the length here does not change. It's still going to be 1/8, right? This dimension stays the same. It's this dimension that changed. So the width is now 0.75, but the length is still going to be 1/8. So for these uniform distribution problems, you're going to have to calculate the height of that rectangle every time. And you can see what the shortcut is. So whatever the width of the rectangle is, 1 over that will end up being the height of that rectangle in order for the total area to equal 1. Right. And then I multiply these together. So I have 1/8 times 0.75, which gives me this crazy probability here. Let's see. Well, I guess that's okay. I was going to say I should have put the decimal first, but actually I like to have a 0 in front of the decimal as well. So I'm trying to get into that habit of doing that. 0.09375. All right. And so that would be the probability of the wait time being less than 0.75 minutes. All right. Let's do another couple of problems off of this example, because you're going to have a few of these on the homework. Unfortunately, the problem will be different every time. So this time, the range of values is 0 to 8, but then when you go to the next problem, it might be 0 to 5, and then the next problem might be 0 to 10. And so you're going to have to constantly keep adjusting the height of your rectangle. On the test, and what I'm about to do on the video is let's just stick with these same numbers so that we don't have to recalculate the height every time. And let's do a couple more probability questions here. So what about asking, what is the probability that the wait time will be greater than, let's say 5.5, just making up a number. All right. So going back to this chart, again, I'm really limited in the number of colors I have access to. I'm going to try red, even though the axes are in red. So 5.5 would probably be somewhere about right here. So we draw a vertical line from that number up to the top of the rectangle. And I want to find the probability that the wait time is more than that, which means I want the area to the right of 5.5. That will correspond to the probability that the wait time is greater than 5.5. Area is going to equal length times width because it's a rectangle, right? So keep that in mind that when we move on to the normal distribution, which is the main topic of 6.1, it's not going to be a rectangle anymore, so length times width is not going to work once we switch to a different shaped graph. But for the uniform distribution, we get rectangles, and the area of rectangles is always length times width. All right, so in this case, the width is going to be from 5.5 to 8. So to calculate that width, you can just subtract 8 minus 5.5, which gives me 2.5. And so that's the width of this rectangle that I'm trying to find the area of, which corresponds to this probability that I'm trying to find. Right, 2.5. The length is still 1/8, right? The length of this rectangle, the height of it is still 1/8. That will be the same for every problem that we do, as long as the range of value stays 0 to 8. The length will continue to be 1/8 every time. And so I'll multiply these together. So 2.5 times 1/8. And that gives me 0.3125. So there's a 31% chance or so of the wait time being more than 5.5 minutes. All right. The last example I want to do is finding the probability between two numbers. So far, every example has been from the edge to a particular number. But sometimes they'll ask you for the probability between two given numbers within that range. So here's another example. The probability that x is between, let's say, we'll just keep it simple this time, between 1 and 6. All right. So what's the probability that the wait time, if we randomly pick one scenario that the wait time in that scenario is between 1 minute and 6 minutes. That's what we're trying to find the probability of here. So that means we want to find the area under the curve, under the graph, between 1 and 6. So here's 1, and here's 6, just past 5.5. I want to find the area between 1 and 6. All right, so that area is going to be that probability. The probability is the area. That's the big theme for chapter 6. That if you want to find a probability, you find the area under the curve that you're working with. In this case, our curve is really just a horizontal line. And when we put lines at the boundaries, it forms it into a rectangular shape. But the actual graph itself is just that horizontal line right here at 1/8, right? So that'll be length times width. In this case, in every case so far for this example, the length is 1/8, but what is the width this time? So why don't you take a moment to think about it while I redraw these parentheses here. So 1/8. All right, so the width, we're going from 1 to 6. So the gap there is 5. Right. So the width is 5. Again, you can subtract. 6 minus 1 tells me that the width there is 5. And so I'm going to get 1/8 times 5. Let's see what that gives me. So, which is just 5 divided by 8 essentially. And so we're going to get, whoops, thought I had the pen active. We have 0.625. So about 63% chance that the wait time will be between 1 and 6. All right, so that's how the uniform distribution works. You'll have a few of those on the homework, and you will have at least one, probably just one question on the uniform distribution on the test if you're in my class. All right, let's take a look at the next topic. A standard normal distribution has 3 properties. Its graph is a bell-shaped curve, just what you see here on the screen. And that's what makes it normal, right? So this is a normal distribution. If the graph is a bell-shaped curve, that's what we describe as a normal distribution. To be standard, it has to have these other 2 properties. So those didn't really go to the same place. All right. So these next 2 make it a standard normal distribution. The mean for a standard normal distribution has to be 0, and the standard deviation for a standard normal distribution has to be 1. So in 6.1, we're going to be looking at standard normal distributions where we have a bell-shaped curve. That's what makes it normal. But the mean is 0 and the standard deviation is 1. As you can imagine, the times that naturally occurs with like a regular set of data is pretty rare, right? I mean, most of the time the mean doesn't equal 0 or the standard deviation doesn't equal 1 or both. The exception to that is for z-scores. And so what's interesting about this is that if you take your data set and you convert them to z-scores, then if it's a normal distribution, the mean of the z-scores would be 0 and the standard deviation of the z-scores will be 1. And so that's what makes this important, because data sets in and of themselves typically don't have these properties, being the mean being 0 and the standard deviation equaling 1. But converting them to z-scores does cause them to have that property. And so you can take any data set that has a normal distribution, convert it to z-scores to make it a standard normal distribution, because z-scores will exhibit all 3 of these properties. The reason, now when we start doing these problems on our calculator, you're going to find there's a way we go about doing that. We type some things in and get our answer. And then in 6.2, we're going to look at normal distributions that are not standard. And to get those answers, we do the same thing. We use our calculator in the same way to get the answer. And you're going to wonder, why do we separate these? Why do we have one section on just standard and another section on regular normal distributions, if you will, like, other types of normal distributions? And the reason is because before technology was widely available, you would have to use charts to determine probabilities, or use calculus to do it. And in this class, you don't need to know calculus, but just to let you know what the math that makes this work is calculus. So because this works like a uniform distribution. If I want to find the probability between two values, I have to find the area under the curve between those two values. So if I want to know the probability of getting a value between 1 and 2, I would want to find the area under the curve between 1 and 2. But it's not a rectangle. It's this very complex curve. And the math involved to find this area requires calculus. That's what calculus does. There is an operation in calculus specifically designed to find areas under curves down to the axis. It's called integration. And so if you ever take calculus, you'll learn derivatives first, and then you learn integrals. And integrals give you the area under these complex curves down to the x-axis. And it's, there's a lot of things you have to learn in order to do that, especially with this function, because the normal distribution function that creates this graph is pretty complicated in and of itself. And then to have to do calculus on that complicated function, it's difficult. Thankfully, we'll have our calculators to do the calculus for us. So we won't have to learn calculus to get these answers. The calculator will do the calculus for us and give us the answer that we need. But before there were calculators widely available, there were charts of values. You can still find them. So if you look on Google for a standard normal distribution probability chart, you'll find them still out there, and they're still in use. In fact, we were using them 5 or 10 years ago still. So I've had to kind of transition my methodologies, my teaching habits from the charts, because that's the way I was taught and that's the way I was teaching. So you would look up these values on the chart, but the chart only worked for standard normal distributions using z-scores. So you would start with this material where it's already standard, so you don't have to worry about the z-score aspect of it. And then in 6.2, you would add the extra layer of take your data values, convert them to z-scores first, then you can look up the values on the chart again, right? And so that's why there's two separate sections. But for you, it's going to really kind of blend together, and it's not really going to seem to make a lot of sense because on a calculator, the methods are going to be the same for both types. All right. So this is a standard normal distribution. This is how we find probabilities using the standard normal distribution. We find the area under the curve just like the uniform distribution, but because the top of the curve is not just a rectangular shape, but it's a complex type of curve, calculus is required to get that area. In lieu of learning calculus, we are just going to let our calculator do the calculations for us. And the function on the calculator that finds this area for you is normal CDF. Right. So to find it, and I'm going to record a video for, calculator information for chapter 6 at some point, hopefully soon. I'm running out of time. I'm recording these as part of a summer class, and the summer goes by really fast, and I probably should have done more of these before the class got started, but I didn't get as far as I wanted to, and now I'm like scrambling to try to keep up recording multiple videos wherever I can find time to do so. So I'm going to try to record the video for like the calculator part of this section. Sorry, I feel like I'm not talking very well right now for some reason. So, but anyways, you go to distribution on a TI-84. So look for my calculator video, and on there it should explain how you get to the distribution menu. It's the same menu that we use in chapter 5 for binomial probability distribution. So you'll see normal CDF in that same list. All right. So you go to normal CDF. Now, again, I have an older TI-84 where you have to type in the inputs without prompts. And so you have to remember the order that the inputs have to be typed in. And maybe I'll do this over here. So you want to use normal CDF. So it'll be normal CDF. Then you type in the lower bound, which is the lower number of the area that you're looking for, right? You're trying to find the area between these two values. The lower bound is the lower number in the range that you're looking for the area of, right? And I feel like I didn't really do that W very well. So lower, I still didn't do it very well. Lower bound goes first, comma, the upper bound. right? Then you type in the mean and then the standard deviation. Now, I'll tell you a secret that if it's already a standard normal distribution, you actually don't have to type those in. But it's a good habit anyways, because as we transition to non-standard normal distributions, you'll have to type in the mean and the standard deviation each time. So you might as well go ahead and start doing that. Now, if your calculator gives you prompts, it'll ask you for the mean and the standard deviation every time, and you actually have to put it in there. But I think the default value is 0 and 1. And then you have to change it if you want to switch it to something else. All right. So this is how you use normal CDF, and it'll find that area under the curve. So let's go ahead and do that for this one. So my lower bound here is 1. That's the lower number in the lowest number in my range. The upper bound is 2. That's the highest number in my range for which I'm looking for the area between. I don't know. I'm trying to think. All those prepositional phrases, I don't know if I'm using the right prepositions in the right order, but hopefully that makes sense. So the lower bound is 1 for this area right here. The upper bound is 2. Assuming this is a standard normal distribution, the mean is 0 and the standard deviation is 1. So that's what you would type in with normal CDF. And let's see what answer we get from that. So I'm going to go to distribution. Normal CDF is pretty close to the top. And then we're going to have the lower bound is 1, the upper bound is 2, the mean is 0, the standard deviation is 1, close the parentheses, and I get 0.136. Well, I don't know, I'll go four decimal places. And the reason this is kind of my habit, even though I know our rule of thumb is for probabilities, keep 3 significant figures, on those charts, the charts list the areas out to 4 decimal places. And so that's kind of my habit when I do these probabilities, is I want to go 4 decimal places because of those charts that I was so used to using. It's also why I like to have 2 decimal places for z-score, because on those charts, the z-scores are listed out to 2 decimal places. So it really has kind of informed my habits regarding these calculations. All right, and so that would be the area. This is the area that I have shaded in right here, which corresponds to the probability that x is between 1 and 2. Right. So this is the probability that x would be between 1 and 2. It's that area which is also that probability, because the area under the curve is the probability, right? That's the association we're making here. We're encoding the probabilities for these continuous random variables as areas in these graphs. So anytime you're finding an area, you are finding a probability. Anytime you want a probability, you want to find an area. All right, so let's take a look at some examples. And there's 2 main types of problems that we're going to see in this section and the next section. One is, here are your bounds, the lower bound, the upper bound. Find the probability. The other one is, here's the probability, find the boundaries for that probability. And so you're going backwards from the area, from the probability, back to the random variable values. And we'll talk about how to do that when we get to that example. So here's a scenario that this textbook concocts so that we have a standard normal distribution in a natural way. So we're not having to convert to z-scores here. The situation is just naturally a standard normal distribution. The Precision Scientific Instrument Company manufactures thermometers that are supposed to give readings of 0 degrees Celsius at the freezing point of water, because 0 degrees is the freezing point of water. But now this, we don't want to get into it, but if you take physics or whatever, the actual freezing point will also depend on your altitude because it's affected by pressure and all that stuff. So we're assuming we're at, sea level, and I think at sea level, the freezing point of water is 0 degrees Celsius, right? So that's where they're testing these thermometers. So if the thermometers are working properly, then the thermometer should read 0 degrees when water is freezing, at the freezing point, all right? Assume that the mean reading is 0 degrees for their thermometers, so their average reading is 0, like it's supposed to be, and the standard deviation of the readings is 1 degrees. So there's some variation. So the the thermometers only, they don't always give the exact right reading. They might be a little bit off, but that can be okay. Now this is supposed to be precision scientific instruments, so probably that's not okay. But I'm just thinking of like, if it's like a mom and pop, just make these kind of cheapo thermometers. It doesn't have to be perfect, right? It could be off a little bit, and maybe you're still willing to sell them, right? So let's also assume, in addition, that the readings have a normal distribution. So we have a normal distribution with a mean of 0 and a standard deviation of 1. That makes it a standard normal distribution, right? So we're told it's a normal distribution. The mean is 0, and the standard deviation is 1. All right, so here's the question. If one thermometer is randomly selected, find the probability that, at the freezing point of water, the reading is less than 1.27 degrees. Now, the thermometer should have a reading of 0. That would be the correct reading. But again, these thermometers are not perfect. They might be a little bit off from the reading that they're supposed to have. So given the mean and the standard deviation for these thermometers, what's the chance that if we pick a thermometer at random, that the reading is less than 1.27 degrees? Now, you could try to just plug in the numbers into your calculator with normal CDF, but I would highly recommend, now this is again an old habit because from using the charts, this was a really helpful thing to do, but I think it's still helpful even with using the calculator, is to draw a picture of the area that you're trying to find, right? So let's draw a normal distribution. It's going to look like this. Oh, that looks really bad. Looks like I don't know, not into zodiac stuff at all, but I was born in October. I'm a Libra, and I know that's the symbol for Libra looks something like that. It looks maybe too much like what I've just drawn there, but that's supposed to be a normal distribution. The mean is in the middle of the normal distribution. In this case, that mean is 0. So we're going to have 0 here at the middle. And then we're interested in the probability that we get a thermometer reading that's less than 1.27 degrees. So I'm interested in, I don't know why that mark went way out there. I'm interested in 1.27, right? That's a really critical value in this calculation. So I want to mark that on my graph. It's positive, so it'll be to the right of 0. So 1.27. And I want to find the probability that a thermometer has a reading that's less than that number, which means I want thermometer readings that are to the left of 1.27. That's the numbers that are less than 1.27, which means for the probability, I want the area to the left of 1.27, all the way to the left. Now, this is something that bothers students about the normal distribution. So I'm trying to shade in the area to the left. It includes this big area here in the middle, but also it keeps going into the left tail. So that's the terminology we have for the description of the graph. We have, I don't even know what it's called, the middle part here, I'm sure has some name, the peak maybe. But then then it kind of tapers off as you go to the left and to the right. We call those the tails of the normal distribution. So this is the left tail. Whoops, kind of was about to write an R because I was about to say this. This is the right tail of the normal distribution. So this particular probability we're trying to calculate goes forever to the left, into the left tail, which extends forever. So if you look at this drawing here, it does a better job than what I drew, but it approaches the axis as it goes to the left, right? So here's the left tail right here, and it gets closer and closer to the axis, but it never touches it. So whenever we're drawing these pictures, we want to make it clear that the graph never actually reaches the x-axis, but it will continue to get closer and closer and closer. We have a name for this that you might have learned in college algebra called an asymptote, right? So the x-axis is an asymptote for this graph. To the left and to the right, the graph approaches without crossing or touching, right? It gets closer and closer and closer forever. And so it goes to -3, -4, -5. Now, as you get out to those larger numbers, I mean, well, those are technically smaller numbers, but as you get to like -4 and -5, the graph smushes so close to the x-axis, it never touches it, but it gets so close that there's really not much area left to find there. And so the probabilities get vanishingly small. And so the probability of getting a thermometer with a reading less than -5, for example, is practically 0, but it technically isn't exactly 0. There's some non-zero probability there. And like I said, that bothers students because it keeps going, -10, -20, -30. those temperature readings would never happen. The probabilities are going to be like 0.000000 with a bunch of zeros, 1, like 1,000 zeros and then a 1, right? So basically impossible. But it never actually hits 0, right? The area, there's always an area there. Again, it's the weird thing with infinities, right? So, yeah, so that's just the nature of it. Now, so I've had students ask, like, for instance, I've done normal distributions with like test scores, right? And so let's say you have a normal distribution where the mean is 70, and then you have the tail that goes out from there. So as you go to the left, you look at test scores that get smaller and smaller, like 50, 40, 30, and you know that test scores can't go past 0. So the reality of it is that at 0, that's the last possible value you can get on a test score. It can't dip below that, but mathematically, with a normal distribution, the graph continues into the negative values, even though you can't get negative values for test scores. And so I had a student ask me one time, they were kind of bothered by that. They're like, but, you can't go past 0, so shouldn't my lower bound be 0 in that case? And in reality, yes, test scores lower than 0 have 0 chance of occurring. You can't get a negative test score, but the mathematical model we're using to represent the test score distributions require that we continue past 0 for finding the area, because even though it's really, really small, it's not exactly 0, and so there's some probability that exists in that negative region, even though those test scores aren't possible. So the point I'm trying to make here is, for these thermometers, this area is going to go forever to the left. It's going to keep getting, it gets smushed as it goes further down. I can't draw these at all. I'm sorry. I'm trying to make this get smaller and closer to this, but I'm not doing a good job, really. Okay. And so that area is going to get smushed smaller and smaller and smaller, but it goes forever to the left, and there's always some area further to find. The point I'm trying to make here is that when you go to find your lower bound and your upper bound, the upper bound's pretty obvious here. The upper bound is 1.27, right? That's my upper bound for the normal CDF. My lower bound, there technically isn't one, because this is going to keep going to the left forever. And so it technically is negative infinity, right? So this would be my lower bound. Now, I think some calculators actually will let you put infinity. Maybe even the TI-84, but at least, I don't know if it's the model I have or like the earlier models that I used to use, you couldn't put infinity as a bound in normal CDF. It just wasn't that sophisticated to be able to handle that. So my habit is to just pick a really, 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 really small number, like negative 99999, just a bunch of nines. I would say at least 6 nines, if not more, right? If you do like less than 6, if you do like 5 nines or 4 nines, sometimes the answer you get doesn't quite match what my stat lab wants to see. Even though that's a pretty small number, it's just not enough. So I would say at least 6 or 7 nines, or just fill up as much of the screen as you can with nines. That's typically what I do. But I just do 99999, but more than 3 or 4 at least, because otherwise. So this is what I'll use as my lower bound for my normal CDF. But I've had students report to me that they were able to use the infinity symbol that they found on their calculator, and it did the calculation that way. And the answers won't differ much, because this, mathematically, like the area past negative 9999999 is so small that the first non-zero digit would be like thousands of decimal places into the number. It's not going to make a difference in the answer that we get, right? So for the first 5 or 10 decimal places, the difference between negative 9999999 and negative infinity wouldn't show up. And so you're safe to use either one. All right. So to find this probability, well, let me say this. We're trying to find the area. The area we're trying to find is what I've shaded in green here. And so we're going to use normal CDF to do that. The lower bound is technically negative infinity. The upper bound is 1.27. The mean is 0. The standard deviation is 1. But like I said, for my calculator, I'm going to be using, instead of negative infinity, I'm going to use negative 9999999. All right. So that's what I'm going to type into my calculator. So here's what we get. Normal distribution, normal CDF, negative. Now make sure for the negative sign, you don't use the minus sign. So I'm going to do this again, even though it's kind of awkward. So a lot of students, the first time they're doing these calculations, they'll use the minus sign. You don't want to use the minus sign, the one I'm pointing at. There is a different button for a negative sign. I don't know why it's a different button, but it treats it differently, so we have to use this button instead. And it's below the 3 on my TI-84. So make sure you're using the negative sign button, not the minus sign button. So negative 9999999, bunch of nines, comma 1.27, comma 0, comma 1. Close the parentheses. I think if you forget to do that, it doesn't care. It still does the calculation just fine. And I get 0.8980. If I'm going to round to 4 decimal places, it's actually 0.89795. But I want to round to the 4th decimal place. So I look at the 5th one. Well, that's a 5, which means this is going to round up, but it's a 9, so that has to roll over to 0, which is going to bump this 7 up to an 8. So we have to kind of be careful about that. All right, so that's the probability you get. So almost a 90% chance that if we pick a thermometer at random, the temperature reading will be less than 1.27. All right, let's look at the next example. This was supposed to be a short video. I was like, oh, this won't take much time at all. And I'm already at 45 minutes because I just talked too much. I'm sorry about that. Find the probability of a randomly selected thermometer. I'm sorry, I'm not reading the words on the screen. Find the probability of randomly selecting one thermometer that reads above negative 1.23 degrees. So again, I'm going to draw a picture to help me figure out the lower bound and the upper bound, and just to have a sense of the area that I'm trying to find. I need to do a better job of getting closer to my drawing. Okay, so here 0's in the middle because the mean goes in the middle, and that's 0 for these thermometers. And negative 1.23 is over here. And I'm not really happy with that negative sign. Let's try that one more time. Okay. And I want to find the area. I want to find the probability that a thermometer has a reading greater than negative 1.23. The thermometer readings that are greater than negative 1.23 are to the right of negative 1.23. So I want to find the area to the right of negative 1.23. So this area here, which again includes the big peak in the middle, but goes all the way to the right in the right tail forever, right? So again, technically, that's going to go to infinity. And again, it never reaches the x-axis, so we have to carry that calculation all the way out to infinity, but the area gets smaller and smaller and smaller as it does. And, you know, it's a weird thing. You might say, wait a minute, the total area, because this is a density curve, the total area has to equal 1. And it does. It's just a weird thing with infinity that, because it gets small enough, quick enough as it goes to the right and to the left, even though there's an infinite amount of area, it's not an infinite amount of area, how do I say this? Even though the area goes out infinitely to the left and right, it shrinks fast enough that the total area isn't infinite. So it's just a weird thing with infinities that we get in some math examples. Like the one I think of is this really weird concept of like a funnel. If I can draw a funnel. This is getting into like some calculus concepts where I shouldn't have curved it out like that. Let's try that again. Do it like that. Where these get closer and closer and closer, right? I shouldn't circle it, but this is getting closer and closer and closer. Now, if I wanted to paint this funnel with paint, it would take an infinite amount of paint because this is going to go forever to, infinity, right? So these will keep getting closer and closer together forever. So that could go out to infinity. So to paint the surface of this thing, I'd have to have an infinite amount of paint to do that. However, to fill this funnel up with some kind of liquid, it would be finite because these are get closer together fast enough that there's a finite amount of liquid that will fit in there, even though the surface area is infinite. So again, weird things happen with infinities like this, especially infinities involving vanishing distances like this. And so, but the math bears it out, and which can make you wonder, like, if infinities behave that weirdly, can they really exist in reality? Because that just doesn't make sense in reality, does it? But it mathematically does as a mathematical object. So you have a funnel that has a finite volume, but an infinite surface area right there. All right. So it's just weird things that happen with infinity. Anyways, again, I'm making this video way too long by doing things like that. So we want to find the area using normal CDF. The lower bound in this case is negative 1.23, comma, the upper bound is infinity, and I'm out of room, so I'm just going to, well, I guess I can scroll over. I shouldn't be lazy. The mean is 0, the standard deviation is 1. But again, my calculator, I don't think lets me type in infinity. I've never actually tried it. I just stick with 9999999. This time positive 9999999, because it's positive infinity, so I just want a really big positive number to estimate or to as a stand-in for infinity. So I'm going to do normal CDF. The lower bound, remember, use the negative sign, not the minus sign, negative 1.23, comma, 9999999, just a bunch of 9s, 0, comma, 1. And we get kind of a similar, I guess that makes sense, given 1.27 versus 1.23, those are pretty close together. So the area is pretty similar to the last problem that we just did. It's just going in the other direction, but the area is about the same. So it's 0.8907. Okay, and so that'd be the probability of picking a thermometer at random and getting a temperature reading that's more than negative 1.23. And it makes sense that, you know, the bulk of the thermometer should be pretty close to 0. So anytime you're doing a probability here where 0 is included, you're going to get a big probability because, you know, there's a good chance that you're going to pick a thermometer with a temperature reading close to 0 because that's where most of the thermometer should be reading. All right, so let's take a look at this example here and then I have a couple more and then we'll be done. Find the probability of randomly selecting a thermometer that reads between negative 2.00, I guess I'll put the 0.00, and 1.5. So again, draw a picture just to make sure you have a good sense of, you know, what's going on, the area that you're actually finding. 0's in the middle. We have negative 2 over here on the left tail. It goes pretty far into the left tail. 1.5 doesn't go all that far into the right tail, but, you know, gets pretty close to it. And we want to find the area between these two values. So my lower bound in this case is negative 2, and my upper bound is 1.5. And so you're just going to do the same thing. Like I said, this gets a little bit redundant with 6.1 and 6.2 because with the calculator, it's just the same calculation over and over and over. Normal CDF, normal CDF. It's more interesting when you have to use those charts, you know, because there's some limitations with those charts and you have to get creative in how you calculate these areas. So you have to put some more thought into it. So again, that's kind of, these problems are a little archaic, but at the same time, there are some classrooms where they're still doing the calculations that way. And so maybe it makes sense to have this material in here for that purpose. And it's just a good way to introduce the material. So the probability of this happening is going to be this area here, which we can calculate using normal CDF so that we don't have to learn calculus to do it. The calculator does the calculus for us. The lower bound is negative 2. The upper bound is 1.5. The mean is 0. I don't know why it's glitching on me all of a sudden. The mean is 0. The standard deviation is 1. So I type that into my calculator. Now what are you expecting? Are you expecting a big probability or a small probability? Well, look how big that area is, right? And again, it's including the reading of 0, which is the mean, which is the most likely reading to get. So this is actually going to be, I think it's going to be close to like 98% of the thermometer readings will be between negative 2 and 1.5. It's going to include a lot of them. So let's see what we end up getting. Now sometimes my intuition's a little off on these, but that's what my intuition's telling me. So negative 2, comma 1.5, comma 0, comma 1. And I'm actually quite a bit, I mean, I would say I feel like my intuition was kind of off on this one. So it's in the 90s, but not quite 98%. I was a little bit overestimating there. So 91% chance, right, that thermometer readings would be between negative 2 and 1.5. All right, so that is being given the random variable value and finding the corresponding probability, right? In this case, we're going in the reverse direction. We're being given the probability, and we want to work backwards to find the temperature reading that corresponds to that probability. So find the 95th percentile of temperature readings which is the temperature reading separating the bottom 95% from the top 5%. So remember from chapter 3 that percentiles tell you the percent of data values less than the particular data value that you're looking at. So if a particular data value is called the 95th percentile, it means that 95% of the data is less than that particular data value. We want to find that data value. What's the thermometer reading that separates the bottom 95% of thermometer readings from the top 5%? I want to find the thermometer reading where 95% of the thermometer readings are less than that one. All right, so draw a picture of what we're looking for. I could do a little bit better than that. Okay. Again, here's 0 right here. Now, if I want 95% of the thermometer readings to be less than the data value that I'm looking for, it needs to be in the right tail. Right? So I'm going to have a data value over here in the right tail that I don't know what it is, question mark on that. But what I do know about that data value is that the area to the left is going to be 95% or 0.95, right? So 95th percentile means 95%, which means 0.95 as a probability. So the area to the left of this value needs to be 0.95. So in this case, we know the probability. The probability is 0.95 that a thermometer would have a temperature reading less than whatever this number is. What I don't know is what is that number, right? So we have the probability, we have the area, we are looking for the data value x. And the way you will find that is to use a different function on your calculator called inverse norm, which I think is abbreviated INV. So INV for inverse norm, which means do the reverse of the normal CDF, right? It's doing the inverse of the normal function that it has on the calculator. So I don't know if I'm saying that right, but whatever the normal CDF function is, this function does the inverse of that. It reverses it. So this function will take the probability that you type in and convert it back to a data value. Now, the way inverse norm works, again, the newer calculators have a more sophisticated interface. You might be given certain prompts for the inputs, but on my calculator, I don't have prompts for the inputs. I have to remember the order to type the numbers in. And with this calculator, you're stuck getting a certain kind of result. You don't have a choice in the area, the direction of the area that it's looking for, the data value. I don't know if I'm saying that right. In this case, I'm looking for a data value where the area to the left is 0.95. That's all inverse norm can do. It cannot find a data value for the area given the area to the right. So you might say, well, the area to the right here is 5%, right? It's 0.05. Inverse norm can't use that information. It only wants the information about the area to the left of the data value that you're looking for on my calculator. Now, I think the newer calculators, you can actually customize that. But for me, on this calculator, I always have to compute the area to the left of the data value that I want. In this case, that's what I was given. The 95th percentile tells me the area to the left is 95% or 0.95. So you're going to type in the area to the left if you're using this version of the calculator, because that's what it wants to know is what's the area to the left of the number that you're looking for, comma, the mean and the standard deviation. So you have to type in 3 numbers for inverse norm to work. Now for a standard normal distribution, if the mean is 0 and the standard deviation is 1, you actually don't have to type those in, and it will calculate the data value assuming that the mean is 0 and the standard deviation is 1. All right, but again, the newer calculators may require that you type something in for these if it has prompts for them, but it probably defaults to 0 and 1 for you, and then you just have to change them if they're different. All right, so we're going to do for this problem inverse norm. The area to the left is 0.95, comma, the mean is 0, the standard deviation is 1. Again, I don't have to type those in, but I will because it's just a good habit. So inverse norm, that's right below normal CDF on my calculator. 0.95, comma, 0, comma, 1. Close the parentheses, and I get 1.6 0.645. And that is the thermometer reading that separates the lower 95% of thermometer readings from the highest 5% of thermometer readings. Right. So 5% of our thermometers are going to read higher than 1.645. 95% of our thermometers will read below 1.645. All right. So any questions? I need to cut that out. Oh, that's embarrassing. I'll probably just leave it in, but that's embarrassing. That's what I do in class. So like I do a problem and I say any questions, and then I've been tempted to do that many times in recording these videos, and I've avoided it. I think that's the first time I've done that since I've really started recording all these lectures. So any questions? Just a bad habit. Not a bad habit. It's a good habit, but not useful for recording videos. All right. Suppose that for quality control, this is my last example, by the way, so we're almost done. Suppose that for quality control, the company decides to throw out the thermometers with temperatures that are too high or too low, right? Because, they don't want to sell people these thermometers where it's giving a reading of like 3 degrees when it's supposed to be 0 degrees. Maybe that's just a little too far off the mark, right? And it's, you don't want it to be that inaccurate. The company doesn't want to throw away too many, though, and decides that losing 5% of their thermometers would be acceptable, right? So if you just kind of decide, well, if it's more than 1 degree off, I think we should throw those out. You're throwing away a lot of thermometers, right? So think about this, right? So here's the normal distribution. 0's in the middle. And if I only want to keep the thermometers that are within 1 degree, so +1 to -1, right? I should say it the other way. From -1 to +1. You're going to throw away all of these thermometers, and that's actually a big area. That's a big percent of your thermometers. And you're going to get in trouble for wasting, right? You're going to have made all this product and you're throwing half of it away, maybe not quite half, but 30% of it away. Let's find out. Let's just find out how much you're throwing away, right? So if we decide to just keep thermometers that have a reading between -1 and 1, because those are accurate enough, how many are we going to keep? Well, let's calculate that probability, right? So this will be, and again, I have the data values this time, right? -1 to 1, those are the temperature readings, and I want to find the area. So this is where students start to get confused, right? Because now you have to make a choice. Do I use normal CDF for this problem, or do I use inverse norm for this problem? So again, I want to emphasize, if you have the data values and you want to find the area or the probability, that's normal CDF. If you have the probability or the area and you want to find the data values, that's inverse norm. So for this hypothetical I've just proposed, just, freestyling here, we are given the thermometer readings. We're given the data values. We want to find the area or the probability, so that's normal CDF. And the lower bound is -1, the upper bound's +1, the mean is 0, the standard deviation is 1. So let's just do that calculation real quick. -1 to +1, 0, 1. That only accounts for 68% of our thermometers, 0.6826. So if I'm quality control, and I'm not really thinking too far ahead, and I just say, well, it's unacceptable if our thermometers are more than a degree off from where they should be. So we need to throw those out. And they start doing that, they're throwing away, this is the estimate I gave earlier, they're throwing away 32% of the thermometers at that point. I think that guy's going to get fired. They're going to be like, you just threw away a lot of money, right? We produced all these thermometers and you're throwing 30% of them away. You're in trouble, right? So instead of arbitrarily, I would say it's arbitrary, but instead of choosing the thermometer reading cutoffs for what's acceptable and what's not acceptable, and hoping that you're not going to throw too many away, you could do it this way. You could decide how many are acceptable to throw away, and then find the thermometer readings that correspond to that. So this company has decided that they would be willing to throw out the worst 5% of their thermometers. But they want to keep 95% of the ones that they're making. So what's the temperature reading that would help us determine which ones to throw out and which ones to keep, so that we're keeping 95% of them and we're throwing away 5% of them, right? Now, here's where it gets a little tricky, right? If we want to throw away 5%, well, which kind of thermometers are we going to want to throw away, right? There are some thermometers that are going to have readings that are too high, and we want to throw those out. But there also will be thermometers with readings that are too low, right? So if we have a thermometer that's reading 3 degrees, well, that might be too high. We might need to throw that one out. But if it's reading -3 degrees, that's too low. It's just as bad in the other direction, right? So we have to take that 5% and divide it up for thermometers that are reading too low and thermometers that are reading too high. So 2.5% will have to go in the left tail for thermometers that are reading too low and have to be thrown out. And 2.5% will have to go in the right tail for thermometers that are reading too high and have to be thrown out. And altogether, that'll be 5% of thermometers that are being thrown away. All right, so draw a picture of the normal distribution. At least try to. I wanted to keep it, but I don't know, it's just too weird looking. Okay, that's still kind of weird looking, but all right. So here's 0 in the middle. I'm going to throw away some thermometers for having readings that are too high and some thermometers for having readings that are too low. And these will be in the extremes, right? So these will be in the tails of the distribution. And I want the total here to be 5% of all thermometers that we make. So, and half of it will be because they're too low, half will be because it's too high, because it's symmetric. And so I'm going to have 2.5% in the left tail and 2.5% in the right tail. Right. Now, for plugging that into inverse norm, we have to convert the percent into a decimal. And so that means this area is going to be 0.025. So we have 0.025 as an area in the left tail. I don't know why I do my arrows backwards like that. And we're going to have 0.025 as an area in the left tail. Right, in the right tail and the left tail. So we have 2 calculations to do, basically. And by doing this calculation, we will find the thermometer reading, which is what I'm looking for. What's this thermometer reading that separates the ones I want to keep from the ones that I want to throw out? So I have the area. I want to convert that into a data value so I'll know where the cutoff number is between the ones I keep and the ones I throw out. To do that, I have the area. I'm looking for the data value, so we need inverse norm. So to find this number, we use inverse norm. Now here's where you got to be careful. On your calculator, maybe if you have a newer one, it might let you pick. Is this the area to the left or the area to the right? And you can choose. And you can say it's 0.025. That's the area to the right of the number that I'm looking for. And that's fine. My calculator doesn't work that way. This number has to be the area to the left of the data value that I'm trying to find, which is not 0.025, right? 0.025 is the area to the right. Inverse norm on my calculator needs the area to the left. So to calculate the area to the left, it's an easy calculation. If you have 0.025 to the right, then how much area would be to the left of that number? I'm talking about this entire area that I'm shading in black to the left, all the way through the left tail. I'm not stopping here where I've shaded in this other 2.5% because I want the area completely to the left all the way through the left tail. And to find that area, it's going to be 1 minus the area to the right. It's a complement, right? Either the thermometers will have readings less than this particular value or greater than it, right? And so it's a complement. And so the probability of having a thermometer temperature reading less than this number is 1 minus the probability that it's greater than that number. And we know the probability that it's greater is 0.025, right? That's the area to the right. That's the probability that it's greater. So the probability that it's less than that will be 1 minus 0.025. And that'll give me the area to the left of the data value that I'm looking for. And so this is going to be 0.975. And that's the area I need to use in my inverse norm. Comma 0 for the mean, comma 1 for the standard deviation. And this is going to give me a cutoff value of inverse norm, 0.975, comma 0, comma 1, 1.96. So that's the upper cutoff. That's the upper bound for what we will keep of our thermometers. So when we test these thermometers, If the reading goes above 1.96, we're tossing it out. We're throwing it away. And that means we'll end up throwing away 2.5% of our thermometers if we do that. But we also want a bound on the other end. And so I want to find this value here. What's the cutoff for being too low, right? This is the cutoff for being too high. So if it goes above that number, the thermometer is reading too high, it's not reliable enough, we have to throw it away. What's the cutoff value for being too low? Again, you have to do inverse norm. But this one's going to be, I did this one first because it was going to be more difficult. This one's going to be easier because we already have the area to the left. So for this particular data value, the area to the left of it is the 2.5%, which is 0.025 as an area. The mean is 0, the standard deviation is 1, and I'm just, because this video is already longer than I wanted it to be, I'll just tell you. And this only works because it's a standard normal distribution, and because it's centered on 0, we have a symmetry at play here. So if the area and the tails is the same, then these data values will be the same. It's just one will be positive, one will be negative. That only works if the mean is 0. So when we get to the next section, you won't be able to use this shortcut of just calculating it once and then taking the negative as the other answer. Because if it's not centered at 0, it won't quite work that way. So, but in 6.1, if they ask you to find a value in both tails and the area is the same in both tails, the numbers will be the same, but one will be positive, one will be negative. So our cutoff value for thermometers that are reading too low is negative 1.96. So anything that reads lower than that, we throw it away, and that will mean that we throw away 2.5% of our thermometers for being too low. And so we will keep thermometers with readings between negative 1.96 and positive 1.96. And we will throw away everything else. And by doing that, we end up just throwing away 5% of our thermometers rather than 32% of them, right? So this would be a better way of managing waste and also increasing accuracy and reliability for your product, right? So you're giving them your more reliable products, but also making sure you're not throwing out too many and wasting resources and revenue, right? Because by throwing those thermometers away, you're losing revenue on that. But anyways, I'm not a business person, so I won't get into the whole business thinking on that. That concludes the video on section 6.1. I'll see you in the next video for section 6.2.